Okay, so yeah, happy Monday everybody. So for the last couple of streams I've been looking at more issue triage stuff, and there's still a little bit more of that I want to do, catching up on issues that built up a little bit while I was working on consulting projects, and then just getting some of the maintenance chores cleaned up, like in particular the Python 3.13 compatibility, the Cython 3 compatibility. But now I want to circle back to this thing I was working on before around getting spaCy up to date, or getting spaCy migrated to use PyTorch instead of the current way that we use, that we implement our models using our machine learning library Think. So as I said in the last streams about this, there's a couple of motivations for this. One of them is that it'll just reduce the amount of software that is kind of particular to spaCy, and therefore reduce the maintenance that we have to do. So that's definitely a big win. The other thing is that I think we can get a bunch of performance improvements because the way that we have the models implemented at the moment prevents us from using standard PyTorch optimization tools that would expect everything to work within one computational graph. So the approach that I was kind of exploring when we were looking at this before, and that I think seems pretty promising, is to have a different implementation for the pipeline that has one computational graph for all of the models. So if you have, say, a parser, tagger, and a transformer model, all three of them would be within the one PyTorch computational graph, and then when you go to optimize it, you just optimize that one computational graph instead of doing it the way that we do at the moment, where there's a bunch of different calls into the optimizer, which makes things more complicated and means that our software framework has to kind of take over coordination of that. So there's this change introduces a bunch of sort of intermediate questions. One of them, because it is a fairly significant redesign, so one of the issues that comes up is around the way that the component lifecycle. So in Think, we have this component lifecycle where there's initialization, and then that's where you kind of set the weights, and then you've got another phase where you do the optimization. Or when you're loading it back, you have a phase where you first create the objects, and you don't initialize any weights for them, and then you load back in the weights. So you deserialize separately from when you actually create the objects. So this works well with the config system, and it's a design that's been working for this period, but it's not exactly how PyTorch works. And there's a little bit of incidental complexity in the way that the config works specifically with this that I want to address that should make things easier. So in particular, when we're doing this, we're going to have a lot more, with the new PyTorch way, we'll have to support paths a little bit differently because there'll be more times where you want to initialize with labels, or just pass in data into the models this way. And at the moment in spaCy's config system, this is actually a little bit painful. So in spaCy's config system at the moment, you can't pass a path into the initialization itself. Instead, what you have to do is, you can't pass a path into a component constructor, or you can't use a path at runtime. Instead, you have to put everything into the initialization phase, then that gets stored out into the model, and then the component actually reads it back out. So what I want to do is address that issue by introducing a feature in convection where if you have a path that's referenced in like this path section, the convection will basically be able to store that separately for you, or the spaCy when you're actually, so I need to review this again and basically visit where I was, and then hopefully we can get at least that feature done, or figure out another place to start with this. So yeah, all right. So let's see. So picking this back up, where was I? So I had everything in this kind of sandbox, and this is where I was kind of working on things. So let's see here. What do we have? So this is a sketch of what components would look like using this PyTorch approach. So we've got our base component. The call and predict and set annotations is as before. Then we've got this replace model to dict, from dict, etc. So how does this actually look here? All right, and then we've got this pipeline class. So this is a different. This is a new sort of abstraction element. Notice doing here. Actually, wait. This is the same as the language. Yeah. So this is just the language. So the difference here is that we've got one ML object, and then that's owned by the pipeline in this design, whereas in spaCy at the moment, all of the ML is owned by the individual components. So if you've got a tagger, it owns its model. If you've got a parser, it owns its model, etc. So what we want to do is have a single computational graph, like this single torch.nn.module, and then the components will kind of know how to access their part of it, or the components will connect to different sort of outputs of it. So let's see here, we've got our components. That's how we get pipe, and then when we add a pipe, we go here. Let's see. Component.model is not none. Right. So if we're adding a component and it's already got a model attached, then we go and register its model with the main computational graph. Okay, and then this note about how we do these things with object reference. Okay. Yeah, this is kind of just as before. All right, so here's how we're going to process a batch. We run the batch of documents through the ML, so we get the ML outputs. Then for each component, we get the predictions from our model specific to that component, and then we call the component's set annotations. So what we don't have anymore is something like the component.predict, I guess. All right, still just reminding myself on where I got to with this. Okay. All right, and then this is the serialization. So let's keep looking here. So here's what we had with the models. All right, model for a component takes a batch of documents and optionally their embeddings as inputs. If embeddings are not provided, an encoder must be provided that calculates the embeddings. All right, cool. So this is a model for something like, a tagger or a parser or a text categorizer, etc. And it has support for running in two different modes. In one mode, you get the embeddings as input, This allows the embeddings to be calculated separately, at the beginning by something like a shared transformer layer, and otherwise you run the encoder for them. Okay. Alright, so that's how. So how does this look for a tagger specifically? Okay, so our layers here. This is a simple tagger model that we run a linear layer on top of the embeddings. Then we'll just call a ReLU layer, and then run our linear here, and then we're going to softmax that here. So yeah, then when we call it, we go forward, we get our logits, then we get our predictions, and we output this. Arguably we should be outputting the logits here as well, but alright, and then how does the whole pipeline work? So let's see, we've got our components. Yeah, we register a model, renaming, removing, disabling, etc. Then when we go forward, call our embeddings, and where's our embedding model? What does that actually reference? Okay, so so it's the part that we have to think through. We've got these outputs. Yeah. Okay, so if we're not disabling something, then if the component isn't disabled, then we go and call it. Okay. So yeah, let's say this note here. We don't save out the component models when we serialize. These are serialized by the components, and the pipeline has to add them back. This way the deserialization process matches the way that the object was constructed. Yeah, so I forgot about this this solution. So yeah, I remember this was a nice thing that we got to when we were looking at this before. So the problem with this stuff is it's very convenient to have shared layers by basically keeping the same object reference in two places, or two references of the same object. So giving the components a reference to some layer that we own. The issue there is that when we serialize and load it back, we want to make sure that the same relationships happen. So if we just serialized everything, then it's more awkward to get the component to sort of pass those back out to the components. Whereas if we do it this way and let the components serialize those parts of the model, we get to have the same thing happen when we first create the object, and then when we're loading back in. So let's see. So what do we have to bytes? Yeah, That's cool. All right. All right. So maybe I shouldn't work on this, dive into this config issue. Maybe it's nicer to get this sort of sketch working. Let's think through what that would actually require. So yeah, according to the notes here, we've got stuff like labels, then questions of scoring and training. So the training seems relative, seems, I can imagine how that works. Let's think through how we would do something like labels. Now, do we want to pass in labels when we create the tagger? Let's go back out to, all right, so pipeline. So let's think through. We've got our tag here, right? So let's go to a little scratch of like. Let's think through what we want. Okay, so let's imagine that we're doing this kind of the same as we were before. Instead of these load and blank and stuff, we'll just say, from spaCy import pipeline and tag a component textcat component. All right. So let's imagine that we go npm with pipeline. Then, what are we doing with our tagger? So, at the moment in spaCy, we have something like this. So okay, so I'm quite fond of this thing that we've always had in spaCy of being able to add the labels at runtime. I'm not sure how useful it is to most people, but probably there's some reliance on it in the community because it's always been there. It's been there since before spaCy 1. Like in spaCy v0, we had this sort of thing. It was actually more useful in the old days when the training story was a bit different and there was more of a workflow recommended around adding new labels to existing models because we didn't have transfer learning in the same way that we do now. So all right. So if we want just so I'll say specify for design sketching. So let's see, we would have let's see, we've got our tag, we've got our blank, we've got our empty pipeline here. Then let's imagine that, we're passing in our tokenizer as before. Now we're going to create our transformer. Yeah, and then okay. Then we'll go text cat component. Okay, so the question is, when do we create the model? And then we would do something like add pipe transformer. And then yeah. All right, so there's nothing in thinking about that though. So So yeah. Okay, so then let's say that I set annotations part. What are we actually doing here? And then yeah, so we'll do something like this. Scores, then for doc scores in zip batch scores equals okay, then yeah. Okay, so Oh. Yeah, okay. So what did I do here? Oh yeah. So this is where, let's to make this practical, ac.tokens import dog. So yeah, to make this practical, we'll operate with spaCy's doc object, and then yeah, we'll want to operate with its tokenizer as well. So yeah, we want to start moving this towards some example code that we can actually run, and in order to do that, it's time that we transition at least parts of this to use spaCy, because the hell does it make sense to implement a tokenizer, to implement a doc object, etc., etc. We're not inheriting unnecessary complexity here from using spaCy's types. So yeah, let's start transitioning the sketch out to using these things. And what we'll do here is we'll use some of these primitives without using spaCy's language object, and without using any of the component implementations, and without using any of the spaCy's ML stuff. We'll implement sketches of those things so that we can explore this PyTorch design. This will also let us use spaCy's scoring stuff, which is nice. Alright, so I've got that. Yeah, so now we have to make this other change over here, spaCy, and scotch. Alright, so we've got our stuff here. Blah, blah, blah. Okay, that should be fine. So now what's the deal here with the embedder? What have I done here? Embeddings, right. So yeah, that's it. An object. So yeah, I guess we need a separate thing. It's not the component model to handle, a part that just returns these. Or should this just be a direct torch.nn model? Not sure. I think it makes sense to have it as, it has to be a wrapper, because we want something that's able to take the doc objects. So in our pipeline here, we need something like I guess I can call this predict, or embed, I suppose. Batch. Okay. Yeah, and the same trick would be done here, where we've got our model there, and when we add it here, that's when we'll have our ML take it over, I guess. So let's see, embedder. So, thanks. I really don't know whether it's awesome content, and I so much so that I wonder whether that's sarcastic, but I'll take it at face value. So, mostly I'm actually doing this for myself to a great extent. It already helped me before to go back over the previous session and look over it, and just kind of keep up to date with where I was. I find it easier than taking enough notes, and over time I think this will help more people get involved with the library. So. Alright, so I've got this as before. So the question is exactly how we want the embedded to interact with the components. We haven't thought that through in enough detail. Let's see, we do a batch. How do we do this? Do a batch. Alright. Yeah, so we make our doc, all ML outputs. Okay, so actually, I had the wrong idea with this. Yeah, the encoder is actually owned by the component model. We don't need to have a separate embedded here. So, oh wait, no, we do. How did this work? Let's see. We've got component model, tag model, this pipeline model. That's what I've got wrong here. So this is not that. We've got a pipeline model class. Okay. So it probably is actually awkward if we don't have some sort of handle on the embeddings, because there's various times where you do want to talk to, that embedding layer, and if we just have it as this sort of amorphous property of the of this pipeline model, I think that'll be less convenient than actually surfacing at a top level like this. So I do think it makes sense to do it this way. Cool. So I guess this is the question of when we actually create this thing. So let's go self.ml equals and yeah, okay, so self.equals pipeline model and So alright, so let's say we do it this way. Okay, so go here, yeah. Let's see, what are we doing in the pipeline model? Alright, so yeah, this makes sense. We've got our forward embedding model, blah blah blah, and then output. Okay, so let's keep thinking this through. Try to keep pushing through to an example. I guess I've only got one. Yeah, I guess the example that we need to get working is just loading a transformer and having this tagger model. So let's see. We'll switch over to let's see. Okay. Test embedder. So, as a sort of general note of how I'm going about this, and I think this sort of general task is a good one to reflect on this because it's the sort of larger change that can easily feel overwhelming. Migrating spaCy to PyTorch, well, it's implementing a whole NLP library, or it's a large set of changes. So the way that I manage this is to kind of alternate between top-down and bottom-up thinking. I do the top-down mode first to see, all right, to think about what characteristics I want of the solution, how things will fit together, and just make sure that we're going in the right direction. I think it's important to do the top-down first, because if you're too incremental, then the space of all possible solutions is very large, and you really don't know whether you end up at a design that you like at the end of it. So I do think the top-down's very important. But at some stage, you then switch over and work at it from the bottom up. What I mean by that is pick, from the top down, you've kind of got this tree of objects in the design that we've kind of sketched out. So now we start picking nodes of that tree from the bottom and get them working. So start testing and using some of these individual things. So so here, for instance, what do we need to do to get this working? Well, let's look at this embedder. So this guy wants to have something like, the transformer. And we have this open question here of how we're actually going to end up at this usable embeddings class, and how we're going to do this doc, preparation and stuff. So let's see. Over here, we'll go. So let's start thinking through the tests here. So import PyTest. We'll go test, create embedder, and then okay, all right. So what I'm doing here is, let's just finish fleshing this out. So what I generally want to do in a test is have this sort of parameterized thing. This is nice because it means that you can pass in multiple inputs. Like we want to create a test that works in some number of transformer factories, some number of transformers. We don't want it to be specific to one transformer model or something like that. The parameterize takes this list, and then it'll call the function a number of times, once per item of the list, and it'll make that object. So the question is, why have I made this factory thing? Why haven't I just passed through transformers there? So a lot of the time, you don't want to create these objects in the outer scope. So we don't want to just call a bunch of complicated PyTorch things in the global scope of our module. We want those to be localized within the test. That way, if they fail in some way, or if there's some sort of teardown or resource consumption, all of that stuff happens within the test. Whereas it's quite nasty if you get these failures at the global level because your tests aren't running at all, and you've got to fix that before you can go anywhere. So what we would do is something like this: transformer equals transformer factory. Well, we'll just make transformer. Yeah, okay, and then so, and then likewise we'd have something like batch, and then this would see a batch, then That's our list of blocks. So when we have two parameterizers on decorating the one function, it actually calls the product of their arguments. So if we define two different transformer functions in two different batches, we get 4 tests out of this basically. So let's see, what do we want to do given this stuff? Well, we want to make our transformer, then we want to, we'll initialize our embedder. So just embedder, yeah, then okay, so yeah, then we'll go okay, so let's see. So now, actually, in order to write this this test, you have to start making assumptions about how this embedding class will work. So, yeah, to avoid that, I'll write some dummy functions. So, check embeddings match number blocks. So, let's batch. So I don't normally do this stuff. Normally I would just have these asserts in there, but I want to effectively procrastinate on committing to how we're doing that part. So this is another bit where I'm doing it a bit more top down, and instead of constantly switching over into different details. All right. So match doc sizes, number of tokens, I guess. That makes sense for the number of tokens in the docs in the batch. Okay, and then I don't know. Whatever. So yeah. And check embeddings match number tokens. Alright. So now where's our embedder? spaCy dot pipeline import and there. So now we've got our the sort of basic sketch here. Let's think through how this actually works. So we've got the spaCy curated transformer library to work with for the actual transformer implementations. So I think that's a nice source to work with this stuff. We can't just use the Hugging Face Transformers library. Maybe it's actually less common. No, I think I'll use the curated one because I've already got there's already kind of this example code for transforming it with spaCy. So let's review some of that stuff. I'll switch over to the browser so we can look at it. Okay. All right. Yeah. All right. Where are we here? Curated transformers. All right. So these are the literal, transformer implementations. So for this, we can install like this, and then we're just creating something like this. So usage. Loading a model, blah, blah, blah. So it's basically the same as transformers, but the internals are a little bit more consistent with each other. And I'm just more familiar with the implementations here. So that's why it's, just kind of nice for me to use it at the moment for this sort of quick purpose. Okay. So yeah, that part all makes sense. Now the next thing is actually matching this up to spaCy. So then we go to spaCy curated transformers. So once you've got the actual transformer, there's this additional task of kind of matching it up with the spaCy tokenization, and that's what this part does. So let's see. So here we've got our pipeline transformer. So this has all of this, there's all of this ugly mechanism in spaCy at the moment for sharing the transformer models. So, you want to run the transformer once and have the embeddings used by the other components. So I won't go into this again, but there's this concept of a listener, and it's a way of passing that stuff around. And this ugliness is a big part of what we want to avoid, or the problem that we're trying to solve by moving to PyTorch. But let's look in more detail how we actually get this. So apply to pipelines model to a batch of docs. Transform model output, and then we've got our outputs here. So that's what we're doing if we don't have any tokens in the docs. So then set model all layer outputs, and then model predict. Where do we actually do these transformations? Where does this stuff happen? It's always the key question when you're looking at any code. Like, where's this stuff? Supported pre-trained transformer models. Yeah, okay. So here's our curated transformer. Okay, so the stuff that I was referring to is happening in this implementation in think layers. So there's no logic that we need in this part. This is the part that takes the think layer and plugs it in and interfaces it with the spaCy pipeline. That's not the logic that we're looking for here. The part that we want is this, in this implementation, the part which takes the torch output and interfaces that with the spaCy doc object. So that includes transforming, getting the IDs out of the doc and sort of aligning the doc outputs with the tokenization, and then on the other side, constructing the object that will pass forward into this. So it's actually in the think layer that we have to look here. So we're not looking here. We need stuff here, which is all of these things. So I just did some work that actually makes this a lot easier. I was just in this code, which makes this a nice time to return to this. So this whole operation is no longer necessary. Given the change that I just made, I figured out a way to do without that step, which was introducing rows for white space tokens. So spaCy has this white space tokens, and we don't want those in the transformer. So there was the question of how to handle that. So now that's being done in a simpler way. We don't have to change those things. So let's keep looking. All right. Okay. So this is the sort of thing that we want to do. Alright, reconstructing our model. This is mostly a wrapper around that other internal thing. So yeah, this is a wrapper that makes a think model that holds the internal part. And then we've got this generic build transformer all listener wrapper. Okay. Piece encoder, top to pieces model. Wrapped listener we don't want. Build transformer model. So yeah, as I said, this part's a no-op, so we can remove that. So what we're doing here is this piece encoding. Need to look up what this width span section is, and this part where we remove BOS EOS. So let's not be too hasty about assuming how we want to handle stuff like the beginning and end markers. There's this question of and then we need to investigate that. But we definitely need something like this, which is this piece encoding, which is taking the doc object and returning something that we can actually pass into our PyTorch models. So what sort of format would we want this to be? I think what would be nice is to have a torch module that's kind of a wrapper around. Well, actually, is that a good idea though? Not sure. Maybe it's better to not make that a torch model. To finish the thought, what I was thinking is we could have it be an actual torch part that makes transformers kind of interface with spaCy. The alternative to that is to keep the transformer module being the operating the same way that it did before, and have a sort of non-torch class. So on the one hand, this wrapper class can't really have any parameters or anything, right? Although, actually, is that true? What if it did have parameters? Alright. Yeah, why don't we make this actually a torch module? So let's see. Let's think through what this would look like. Okay, so we've got our underlying model there. Forward. Days, and then we need to look up exactly what we do there. And then format output. Alright, so let's look up this piece IDs. So that's here in tokenization, I think. All right. So the annoying thing is that this part needs to match the transformer part, like they kind of belong together. You don't freely get to mix and match here. So let's review this again. or models, architectures, right? So you've got like a piece encoder here that surely there's some right answers and some wrong answers, right? And then, yeah, let's take another look at this width bounds. Where are we? Yeah, so this is some extra quirks of this that were introduced to handle doc lengths. So this is the origins of this. This stuff go back quite a way. So spaCy transforms, I think, was our blog post. Yeah. So let's see, text, blah blah blah, doc. Yeah. Let's zoom out so it's a bit easier. Yeah, cool. So this is this alignment part. This is actually simpler now because what we do here is we force the tokenizer to actually match the boundaries of the linguistic tokens. So we say that you can't have these overlaps, but there's still this issue of a variable length number of word pieces that match up to these linguistic tokens. Let's go back here to the piece encodings. So let's see, spaCy curator transformers. Transformers architectures. Let's see. I really don't love this this solution. I hate in code when there's a question, there's just like a right answer, and you just have to give the right answer. It feels very wrong to me. So, it shouldn't be the case that you've just got to make these things match, and then there's this tool that sort of covers for that. Great, yeah. Okay, so let's take a look here. Curated transformers models must be paired with a matching tokenizer piece encoder model in a spaCy pipeline. As with the transformer models, tokenizers are constructed with an empty vocabulary during pipeline creation. They need to be initialized with an appropriate loader before using. So construct a callback to initialize a byte BPE piece encoder model. Higher encoder model. Interface piece encoder loader. Okay, so the way that this works is if you're just defining things, like let's say you're making a new model architecture, then you have a choice between, what byte BPE loader or what car encoder loader and stuff to use. If you're loading from the Hugging Face hub, which is almost always what you're doing, or you're loading some pre-trained checkpoint, then these things come sort of pre-cooked. You have to use the one which they use. Okay. Let's see. Let's pop one more up the stack and look at the underlying piece, the curated transformers. Okay, so let's see, usage. Alright, let's look at this. Model weights. Okay. All right. Let's go back to the code. Yeah. All right. Let's see. Where are we here? Okay, so yeah, so yeah, there we go. Manipulate transformers. So that's what we want there. All right. Yeah. Let's just make sure that this works. To transformer. Okay. So that's that part. Now tokenizer. All right. So now. Hey, how's it going? That's cool. Where are we? There we are. Okay. All right. Alright, so that's those two loaded. Now let's look back at the library for the actual usage. Alright, so what are we doing here? Text encoding. Yeah, I really don't think my typing definitely isn't something that I especially pride myself on. I never learned to type as properly as I should have. Okay, so that's all that. Alright, so we've got our input pieces like this. It's like that for PyTorch. Nope. Alright, so what do we want for the device here? Okay, yeah. Alright. Oh yeah, okay. So, what pieces? These. All right. So that's the sort of naive approach where we're calling this with a bunch of strings. Now the question is, what were we actually doing in the spaCy curated transformers part to make sure that that aligns with spaCy? So let's, I didn't switch back over from this. Let's go back here. Yeah. All right. So yeah, we've got this example working now, but this is being passed strings. And the question, so I'm going to look at how we're actually calling that within the spaCy curated transformers library. So let's go back here. Okay, tokenization. So these parts I think are not what we need. Or are they? Okay, so piece ID, for doc. Oh no, this does what we want here. So yeah, okay. So that's how it's working. We're calling the tokenizer individually on each token. Encode as IDs on each bit of text. Okay. Okay, so spaCy. It's easier. Alright, so spaCy IDs. So now we want texts, lister, encoder, or token. Okay, and then we go okay, so now so we don't get this encoders IDs part. What do we actually have here? So we've got the curator transformers, tokenizer, auto tokenizer. So piece to ID. Encode. Yeah, see ya. Okay, so that's the class that we're looking at here. Okay, so we've got this wrapper basically. Let's face tokenizers. So this is the part that we want to be working with, this pre-tokenized input sequence. Any sequence can be either a string or a list of strings. Okay, so I want pre-tokenized input sequence. Okay. So the question is whether this always works, whether we can always do the encoding this way. Let's take a look. So I wonder why this was done this way. There must have been a reason. Because basically the library here isn't allowing this mode that the Hugging Face that Hugging Face supports of passing in pre-tokenized inputs, which is a very useful mode for what we want. So let's see. Let's work directly with the Hugging Face stuff instead of using these wrappers. We might end up running into different problems, but I think it'll be simpler for now. Alright, so let's see. Let's just remind myself of what this. Model, isn't it? Yeah. Okay. Okay, so then texts and tokenizer. Okay, so let's see. Encode batch. I think it's right there. No, okay. Let's go back to the web and go back to tokenizers. Tokenizer. So maybe we can just call it. Yeah, let's try calling it. Okay. All right. So where are we? spaCy IDs, word pizza. What are we calling here? So I thought we could call this with a list of strings. What do we have here? Text, text pair, text just a list, sequence or batch of sequences to be encoded. Each sequence can be a string or a list of strings. Yeah, that's what I thought we were doing. If sequences are provided as list of strings pre-tokenized, you must set is pre-tokenized equals true. Okay. Pre-trained tokenizer fast, but an unexpected keyword argument is pre-tokenized. So pre-trained tokenizer fast. Let's look at this. Pre-trained tokenizer fast. fast tokenizers. Okay, so is this just a lie? What's going on? Am I using a different version? Pig list. Okay, so we've got 4.8.1. Oh, fuck. Okay. So, for some reason they renamed this pre-tokenized to is split into words. Fine. Okay. So now we can go word pacer blah days and then we actually do this afterwards. So let's see. I think we want return tensors. Padding equals true, truncation equals true. All right. What's type list where type int is expected? Okay. So So we're getting somewhere here. Yeah. 2 GPU 0. Okay, all right, so that's enough for now. Okay. Cool. All right, so that's next steps. All right, so I'm not sure whether I'll return to exactly this tomorrow or whether I'll do another day of issue triage, but I am keen to do it. So yeah, maybe maybe I'll continue this tomorrow. We'll see. All right, for now that's enough.